let's go back in time. Let's go back in time to, in some sense, sort of the birth of modern civilization, where mathematics first makes its appearance with the Mesopotamian mathematics. So, in the history of the world, very roughly, sort of cities, large-scale urban centers, start around 3000 BC, and they do so generally around river valleys, where agriculture is able to be performed on a large scale. And prominent amongst these early sort of urban environments are the Mesopotamians, who lived in the area which is now more or less sort of the Middle East, but Iraq and parts of Iran, Lebanon, Syria, Jordan, that area. And as well the Egyptians. And then a little bit later, the ancient Chinese also started becoming interested in mathematics. But their development is a little bit later on, before things got going sort of in an explicit written way. So the earliest mathematics that we know about is from the Mesopotamian area and from the Egyptian eras. And then afterwards, sometime around somewhat later, here around 1000 AD to 0, we have a Greek period, and then followed by an Indian period and an Arabic or Islamic period, and then a sort of European period, later on, around 1400s, middle of the last millennium. Okay, so these are sort of main mathematical civilizations, and in the history of maths, up till relatively recently, people sort of imagined that things sort of started with the Greek period, maybe around 600 BC, stretching to around, say, 300 AD. So the Greek period here is kind of like a golden time of culture and learning, with many famous names. And in times gone past, people thought that the history of mathematics sort of started with the ancient Greeks. Okay? But it's becoming clearer and clearer as we delve into more artifacts, and our understanding of earlier times becomes clear that a lot of the Greek developments really rested on prior Egyptian and Mesopotamian mathematics. Okay, there are these earlier cultures, including also the Chinese, that really predate the Greek things. Also, I should say there was also an Indus Valley, sort of also Indian, sort of early Indian mathematical tradition, also earlier. So today I want to talk mostly about the Mesopotamians and some of their remarkable mathematics. Now, what are we talking about? So there's various groups of peoples. There's the Sumerians around 3000 BC, followed by the Akkadians, maybe around 2400 BC, and then the Babylonians, maybe around 1900 to 1600 BC. And then there's a kind of a fall. There's civilization sort of takes a nosedive, and actually the mathematical record also is much reduced until much later we end up with the Persians, maybe around 600 BC. And then in that same era or area, we have eventually Alexander the Great comes in, sweeps through the area, and sort of institutes a Greek period. So maybe around 300, 350 BC. Okay, and what area are we talking about? We're talking about the area which is roughly southern Iraq. Okay, and there are two great rivers coming in here. There's the Tigris and Euphrates rivers. And then there's the Persian Gulf down here. Okay. And so Egypt is over here. And the Mediterranean is up here, very roughly. Okay, and I've given you a little map so you can kind of see. Iraq would be this little green spot right there. There's the Persian Gulf. And so we're talking about this area in the Middle East, more or less centered around present-day Iraq. All right. And 5,000 years ago, this was a very fertile area. It was called the Fertile Crescent. And it supported a lot of major urban cities. And this was really perhaps the first place where urban life really got going in a major kind of way. So there were lots of cities, city-states, started by the Sumerians. So it's really the Sumerians that start this entire story. And they are a people that we don't know very much about. We don't know where they came from. They just sort of show up around 3000 BC. And they seem to be very remarkable. They develop all kinds of remarkable things, including things like the plow, writing. Writing is developed first by the Sumerians. Beer, women's rights. There's temples. There's palaces. There are canal systems and major irrigation. And of course, there's widespread agriculture. They also have boats. Probably sailboats were probably invented by the Sumerians also. But we're not sure about that, but it's possible. Okay, so the remarkable people, and then eventually the Akkadians took over, and then the Babylonians. And this entire historical era was, until relatively recently, not known about at all, or only known about very modestly. Because historically, the great Egyptian civilizations were the focus of attention for archaeologists and historians. The Egyptian civilization, which was more or less concurrent, was also completely remarkable, and you know, there are all these fabulous artifacts, temples, pyramids, vast treasures, tombs, you know, massive, incredible stonework that hasn't been repeated since. So the Egyptian culture has been fascinating mankind for thousands of years. But only in the last 150 years or so have archaeologists become aware that there's this other culture buried in the sands of southern Iraq. There aren't big pyramids, there aren't big temples left. They did not have stone. Okay, the Sumerians did not have stone. The Egyptians had stone, so they were able to build on a massive scale in a very permanent way. But the Sumerians and the Mesopotamians generally built in clay. So you can still build great things with clay bricks, and they did, but after thousands of years they crumble, and they end up just in piles of rubble buried under the sands. So that's what we currently have. We know that there was a really rich civilization, but most of it is buried in the sands under Iraq. There have been major excavations. And when the excavations, what they revealed is that this is actually a very fascinating culture with actually a very surprisingly advanced mathematics. And the fact that they use clay instead of stone has one great advantage for us, because they wrote on clay tablets. They wrote on clay tablets, and we have hundreds of thousands of clay tablets from this ancient time in museums and collections around the world. Many of them have not been translated yet. They're still waiting for people to study them. The British Museum probably has a couple 100,000 clay tablets from this era. But a lot of them have been translated and studied, and they reveal a fascinating culture, which, besides having all of these sort of important innovations, in particular writing, also was very sophisticated mathematically. And so that's what we're going to talk about today. We're going to talk about the mathematics of the Sumerians, Akkadians, and especially the Babylonians. So it's really under the Babylonian times when this mathematics attained a very high level of sophistication. And we have quite a lot of evidence for that. All right, so let's talk about the mathematics of the ancient Babylonians. And so this is a cumulative story involving the Sumerians, the Akkadians, and the Babylonians. I'm sort of going to express the story as in the time of about Hammurabi, who was the main king in the Babylonian times. So the mathematics in Babylon is characterized by the fact that they had perhaps the most remarkable arithmetical system of all time. Okay. So their arithmetical system was arguably the most sophisticated of all time. Even more sophisticated in some ways than our current system. Why? Because it was a base 60 or sexagesimal system. But it was also a floating point system. So we need to explain this. This is an absolutely remarkable and fabulous mystery about how this ancient people could have developed such a sophisticated mathematics, which was thousands of years ahead of their time, really. Okay, so base 60 means we work with base 10, right? And we have ones and tens and hundreds and so on. So when we write 576, these are the ones, these are the tens, and these are the hundreds, and so on. So, and then we have a decimal point, and maybe we have like 4, so that would be the 1/10, and so on. So they had a very similar system, except it was in base 60. So they had digits, and the digits were from 1 to 59. Digits from 1 to 59, but how were they expressed? So our current system of digits goes back to the Indian mathematics, to Sanskrit, and in around 500 AD is when our numerical system sort of started being developed. So what did these people do? They didn't have 59 different symbols. Okay, they only had 2 different symbols. Okay, and the symbols that they had were a symbol for a 1. And a 1 was expressed by taking a stylus, which is, you can think of as something like a chopstick, okay, just a piece of wood, and a clay tablet, and you just make a mark. You dip the top of the chopstick into the clay, and you just move it down a little bit, creating a vertical mark with a little bit of a triangular top. That represents 1. Okay, so if they wanted to make bigger numbers, so 1, 2, 3, that's how they would make 3. And then if you wanted 4, 5, 6, there would be 4, 5, 6, and then 7, 8, 9. So that would be how they would represent 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 in a row, and then you go to the next one. Okay. Now, what about 10? Well, 10 was the other symbol that they had. They used the chopstick again, or the stylus, and they just oriented from left to right instead of up and down, left to right. And they made a kind of a wedge by making it sort of like this. So they kind of pointed like this and sort of, I don't know, made some kind of mark that looked like this. Okay, that's a 10. So if they want to do more than 10, they'd make 1, 2, 3, that's 10, 20, 30, 40, 50. So that would be 50. And then to create a digit between 1 and 59, they would just put 50s or 10s and 1s together. So for example, to write 38, they would make 3 10s and 8 1s. Something like that. So that would be a single digit for them, which represented what we would call the number 38. And then these digits were placed beside each other, very much the same way we do, with increasing powers, or increasing powers of 60 as we go to the left. So let's say we have a number like 1, 1, 1, maybe 10, 10, 1, and 10, 1, 2, 3, 4, 5. Okay, 6. So that this thing here, what is that? Okay, that would be a Babylonian number. And you should recognize that there are sort of 3 digits. That's a digit. It's got some 10s and 1s. That's another digit. It's got some 10s and 1s. That's another digit. It's got some 10s and 1s. So what are those digits from our point of view? They are, here there's 50, 56, and this would be 21, and this would be 3. That's the Babylonian number 3, 21, 56. Now what does that number mean for us? Well, now that's an interesting thing, is that they really had a floating point system. Okay? And the floating point system, like what we would say a decimal point, it really was not part of the number. There was no actual decimal point. And they were flexible about where the decimal point was. They were flexible about that. So one interpretation could be, this is 56 times 1 plus 21 times 60 plus 3 times 60 squared. Powers of 60 increasing as we move left. So we would, what would we say this is? 60 squared is 3,600 times 3, so that would be, I guess, 1080 plus 21 times 60. 612, 1260, and 56. Okay, so 56. 6, 11, 11, 20. All right, so that would be, 12,116 according to my calculation. That would be our number. That's their number. But, and here's the curious thing, but this same expression could also be interpreted differently, because they were flexible about where the floating point was. So in another situation, this could also be alternately representing perhaps 3, let me write it from the left. Oh no, I'll be consistent. 56 times 1/60th plus 21 times 1 plus 3 times 60. That would be sort of like putting a decimal point here and regarding this rightmost digit as representing the number of 1/60ths instead of the number of 1/10ths. Or, in fact, you could have a lot of other possible values. You could imagine it having a decimal point there, or even the decimal point could even be out here. All right, so this could also represent, let's say, 3 times 1 over 60 plus 21 times 1 over 60 squared plus 56 times 1 over 60 cubed. So they had a flexible approach to their numbers. Okay, so their mathematics was typified by a certain precision and a certain care and sort of systematic approach. So they emphasized procedures. They emphasized procedures. And I'm just going to read one to you. So this is from a paper by Donald Knuth, whom most of you will have heard of, the famous computer scientist from Stanford, who was the inventor of LaTeX, and a major computer scientist person. So he wrote an article called Ancient Babylonian Algorithms, where he was talking about the sort of connection between the ancient Babylonian thinking and modern computer science thinking. And so here's one example of an actual problem that occurs in one of these tablets. And I'm just going to read it to you so you get a sense of what it's like. A rectangular cistern. So it's like a pit, maybe filled with water or something. The height is 3, 20. Okay, so when we say 3, 20, maybe I should put it up here. So, you know, we might represent this with 32156, or typically people express the Babylonian numbers with commas separating the various places. Okay, so that's what he's doing here. So the height is 3, 20, and a volume of 27, 46, 40 has been excavated. So that's a volume. You know the height. The length exceeds the width by 50. Okay, now it doesn't say, but what they want you to do is to find what the length and the width are. Okay, so you know the volume and you know the height. Okay, so you can divide the volume by the height, then you'll know the area of the base. Okay, what do you know also? You know that the length exceeds the width by 50. It's a quadratic equation. So you know the length and the width differ by 50, and that their product is whatever the area is. That's a quadratic equation. Okay. Now what the solution or the text explains is really how to solve this quadratic equation with these numbers. So you should take the reciprocal of the height, 320, obtaining 18. Multiply this by the volume, 27, 46, 40, obtaining 8, 20. Take half of 50 and square it, obtaining 10, 25. Add 8, 20, and you get 8, 30, 25. The square root is 255. Make 2 copies of this, adding 25 to the one and subtracting from the other. You find that 3, 20 is the length and 2, 30 is the width. This is the procedure. All right, so without going into the details, what they're doing is they're explaining a solution, but instead of using x's and y's like we might do to explain what you're supposed to do, they use these specific numbers. Okay? So they use specific numbers to illustrate the procedures. Now, as this problem shows, they are able to solve quadratic equations. So quadratic equations. So it used to be that people thought that the solution of quadratic equations, like the current quadratic formula, is due to Islamic mathematicians around 1,000 years ago. But it's now become clear that actually the ancient Babylonians, 2,000 years BC were well familiar with quadratic equations. So to give you an idea of that, suppose we have the equation x squared plus px equals q. And they thought we now know geometrically about such things. So you can picture this by thinking of x as a length and x squared as representing an area of the square. And then you can think about px as being an additional rectangle added to this with p in that direction. Okay? So this rectangle here totally captures the left-hand side of the equation. So we know what this entire area is. And we want to know what is x. Okay. So they knew that what you do is this. You divide this little rectangle on the right in two. Okay? So now we have two pieces. Now p over 2 and p over 2. And then what you do is you move things so that you now still have half of that, p over 2, and you take the other half and you put it down here. Okay, that's still x and that's x. Okay, so we've just taken this piece here and we've moved it there. Now it's almost a square. And if we add the little corner here, how much should we add there to make things work? Well, that's p over 2 times p over 2. So this area here is p over 2 squared. So if we add that, then we get a completed square. This is sort of like completing the square. So what do we get? We get that x plus p over 2, which is now the area of this bigger square, all squared, is going to be equal to, well, the original amount, which was q, plus the amount that we had to add. How much did we add? We added this little square down here, which was p over 2 squared. So the quadratic equation has been transformed. It's still a quadratic equation, but has a crucially different form now. Now it's of the form something squared equals something else. And now you have the potential of looking up what essentially the square root of the right-hand side is. So the Babylonians had lots of tables. Okay, that was another feature of their mathematics. There were many tables for all kinds of things. Okay, and they relied heavily on these tables. So they would, if they were given a problem like x squared equals something, they would look in their tables to see, tables of squares or tables of square roots, they had both, to see what number squared is what you're required. So we would say, okay, you take the square root, so that x plus p over 2 equals the square root, let's write it like this, square root of q plus p over 2 squared. And for them, a square root was always positive. Okay, that's a positive number. And so therefore x equals square root of q plus p over 2 squared minus p over 2. Okay? So it's a form of the quadratic equation when you start from writing it like this. So this was very familiar to them. It was a standard kind of technology. And yeah, this is almost like 3,000 years before Islamic mathematicians essentially rediscovered the completing the square kind of story in the quadratic equations. Okay, so let me talk about some of the tables that they used that were very important for them. Okay, so they had lots of tables. And their tables were very systematic. They never skipped steps. So if they wanted to multiply, say, multiples of 7, or multiples of 56 or something, they would always start with 1. 1 times 7 equals. 2 times 7 equals. 3 times 7 equals. They would be systematic. Nothing was too ordinary or boring for it to be excluded. Okay? So that's one important aspect of their things. So what tables did they have? Well, they had tables of squares. And square roots. And also cubes and cube roots. Squares were very important. But perhaps even more important than these was the crucial table for them was the table of reciprocals. The reciprocal table. So to understand the importance of the reciprocal table, we have to think a little bit about arithmetic. Okay? When you're teaching young people arithmetic, you teach them first addition. Okay? So if you were going to teach students how to do arithmetic in a base 60 system, that would be pretty straightforward. They'd have to practice working with digits less than 60 and how to add them, and then some carry on and so on. Multiplication is more tricky because you have to worry about how do you multiply 37 by 43, right? Do you want to memorize a 60 by 60 multiplication table? Probably not. Okay? So how did they multiply? And the remarkable thing is we don't really know. We don't really know how they multiplied. Although there are some hints, at least to what they did sometimes. So I'm going to come back to reciprocals in a second. But to multiply, what they did is they used the following kind of clever identity. That A times B is the same as A plus B over 2 squared minus A minus B over 2 squared. Do you all agree with that? If you span this, the A squareds and B squareds will cancel, but there'll be a 2AB over here. Minus 2AB over there with a minus sign, so it'll be altogether 4AB, and we're dividing by 2 squared, so it'll be altogether AB. Okay. So what does this formula do for us? This formula allows us to perform a multiplication by looking up 2 squares. So for example, suppose we wanted to calculate what is 13 times 47. Okay. Well, I've chosen 2 odd ones to make it a little bit easier. So the sum is what? The sum is 60 divided by 2 is 30. So it's 30 squared minus, and the difference is 47 minus 13 is 34. So it's 34. Divided by 2 is 17 squared. So you look up 30 squared on your table. You look up 17 squared on your table of squares. And you just take the difference, and there's the product. So we do know that under certain circumstances, they used this as a way of multiplying. But I don't believe that they use this uniformly. So I'm actually of the opinion that they, and other people are as well, that they actually had some form of abacus. Okay? They probably also used some kind of abacus. But we don't have any record of this exactly. So we have some indirect evidence that suggests this, but we don't have any direct concrete evidence. So it's an intriguing kind of thing that hopefully more evidence will clarify. So anyway, that's at least one way that they could possibly multiply. Now, when you're doing arithmetic, especially if you're teaching young people, you will know that the most challenging operation is always division. Division is always the painful operation, right? And it's painful for us. Why is it painful? Well, let's say we divide 24 by 6. Okay, how do you divide 24 by 6 if you're a primary school student? You remember your multiplication table. You remember, 6 times something, 6 times 4. Yeah, 6 times 4 is 24. So you remember your multiplication table and you say, okay, it must be 4 because 6 times 4 is 24. What happens if you want to divide 24 by 5? Okay, what in the multiplication table, nothing times 5 makes 24, so that's not going to work. So what do? Well, we have this method of introducing decimal numbers. Right? We know how to do this with a decimal calculation. Divide 24 by 5, you get 4.8. Right? Is that right? 5 times 4 is 20. 5 times 8 is 40. So yeah, 4.8. So that's a division that we can do. Because why? Well, because 5 is very pleasant in our system. 5 is one of the factors of 10. It has a special role. 2 and 5 play a very special role in our system. If you want to divide by 2 or by 5 or any products of those two things, it's relatively simple. Because the result of the divisions is going to be another finite decimal. But what if I ask you what is 24 divided by 7? Okay, now it's a little bit more challenging. What is 24 by 7? Well, if you get your calculator, right, it'll spew out some decimal, but you know that it's a repeating decimal, right? This is a decimal calculation which in fact doesn't end. You have to keep going to infinity to actually get the final answer. Now, of course, you know what we do, right? We have an alternate system of numbers aside from decimals called fractions. And these fractions are very pleasantly arranged just in order for us to be able to deal with this kind of division that we can't really do with the decimal arithmetic. So what do? We say, it's the fraction 24 over 7. Now, to a Babylonian, this would have been very suspect, saying, wait a minute. You're dividing 24 by 7, and what are you getting? 24 over 7? You haven't solved the problem. You've just cooked up some fake kind of little symbol to represent this operation which you haven't done yet. This would be very dubious for a Babylonian. In fact, dubious for the old Babylonians. In fact, the Babylonians sometimes did have to divide by 7, and then they would routinely say, it does not divide. 24 divided by 7 does not divide. They recognized that they could divide it approximately, but they were very precise about what they could and couldn't do. They did not accept that their approximate calculation was actually a correct answer. So as far as they were concerned, this thing doesn't divide. So in fact, fractions play no serious role in Mesopotamian mathematics. Quite different from the Egyptians on the other side of the Red Sea. The Egyptians had a mathematics in which fractions did play a big role, and they didn't have a sort of a decimal system. But the Babylonians really were more decimal oriented, except it wasn't decimals, it was sexagesimal. Okay. So what makes their system so interesting is that they were able to exploit the richness of the base 60 system to allow a much wider division than we have. Okay? And so this is the role of the reciprocal table, which I want to tell you about now. So their division was actually much richer than ours because they were working in a base which is much richer than ours. And so they are able to do more. Okay. And it's the reciprocal table that really reveals it. Now, it's actually quite a long table, so I'm not going to write it all, but I'll write some parts of it. Okay, so here's the reciprocal table. They sometimes talk about Iggy and Iggy-B, sort of numbers and reciprocals. Okay, so we have a table like 2, 30, 3:20, 4:15, 5:12, 6:10, 8, 7:30, 9, 6:40, 10, 6. That's the first row, the first column. So what are we saying here? The reciprocal of 3 is 20. Is that correct? If you multiply 3 by 20, what do you get? You get 60. And what is 60 in their system? So that would be like 3 times 20 equals 60. There's what 60 looks like. 60 looks just like 1 for them because they don't have an actual decimal point. They don't distinguish between 1 and 60 squared. So 3 times 20 is 60, 3 times 20, 2 times 30, 3 times 20, 4 times, these are all the reciprocals, so 8. And then it goes on. There's 16, the reciprocals, down to 40, and then 45, down to 121. That's as often they went up to this. And the reciprocal of 121 is 44, 26, 40. So there were a lot of entries, okay? There were a lot of entries. I'm not writing them all down. Numbers and the reciprocals. Number and then reciprocal. Number and then reciprocal. So in order to divide by something, they would look on this table to see what the reciprocal was. Now, you see that not every number is here. There's 7 is not here. What are the numbers that are actually on this table? Maybe I should do a little bit more. 16, 18, 20, 24, 25, 27, 30, 32, 36. And then 45, 48, 50, 54, 1, 1.04, 1.12, 1.15, 1.20. So these are all the numbers which have reciprocals, finite reciprocals in the ancient Mesopotamian system. These are all the regular numbers. Created from powers of 2, 3, and 5. Any power of 2, any power of 3, any power of 5, or any product of such a number in their system, which means that its reciprocal is a finite expression in their sexagesimal system. For us, it's like that, but we don't have the 3. We are working in base 10, so the regular numbers for us are the powers of 2 times powers of 5. Those are the numbers that we can invert in our system. They can also invert 3s, and that makes a crucial difference because now the numbers that they can invert are so much richer than in ours. So division for them was often something that they could do exactly without having to revert to some kind of fraction system that sort of does it, debatably, and without having to rely on some infinite decimal process that actually doesn't end. Okay, so this is sort of the basis of their arithmetic. It was a very rich arithmetic. There was, it was so powerful, in fact, that even centuries, millennia later, when Greek mathematicians and Greek astronomers wanted to make intensive calculations with astronomical data, they went back to the Babylonian system. So even 1,500 years later, the Greeks like Ptolemy would make calculations in the Babylonian system. The Greek mathematics was not as powerful as this ancient Babylonian mathematics. And even later into the Islamic period, Al-Kashi, who was a very important Islamic mathematician, lived in Uzbekistan around the 14th century, calculated pi to some 15 or 16 sexagesimal places. So even then, the sexagesimal system was used because it's powerful. It supports very rich computation. It's absolutely remarkable that this most ancient of people, this very first arithmetic, was so rich. So in my next talk, I'll tell you about an important geometrical aspect of their thinking.